Hello everyone, I am Dr. Shreya Sinha, Assistant Professor of Physics. This video is a part of UGC HRDC Faculty Induction Program 17 assignment. Here I am going to give the lecture for the BSc third year student on the topic of photoelectric effect. And this is the description of the topic. Before starting the topic, student must have some knowledge about the origin of quantum mechanics, what is black body radiation and Planck's quantum theory. After completing this module, a student will be able to understand what is photoelectric effect, what is experimental setup for the photoelectric effect, what are experimental results associated with it, idea of Einstein photoelectric equation which won Nobel Prize in physics later on, and explanation of experimental results based on Einstein equation. Now, what is photoelectric effect? It is a very simple phenomena. When light of certain frequency or higher than a certain frequency falls on the metal surface, the electrons are ejected from the surface of metal. And this phenomena is known as photoelectric effect. And since electrons get ejected due to action of some incident radiation, so these electrons are known as photoelectrons. Let us understand the experimental setup for the study of photoelectric effect. This is the circuit diagram. First of all, we have a glass tube G having two electrodes C and A. Electrode C is connected to the negative terminal of the battery and A is connected to the positive terminal via rheostat. Here rheostat helps to maintain a desired potential difference between the two electrodes. The applied potential difference is measured with the help of a voltmeter V and current is measured by ammeter. Now when light falls on the surface of metal, electrons are emitted and current flows in the circuit known as photoelectric current. And this photoelectric current depends upon the following factors. First, the intensity of incident radiation. Second, the potential difference between the two electrodes. And third, the frequency of incident radiation. Now let us try to understand each one of these factors one by one. First, what is the effect of intensity of light? When we fix the frequency and only the intensity of light is vary, then it is observed that photoelectric current increases linearly with the intensity. It means that on increasing the intensity of light, more number of photoelectrons are emitted by the photocathode reaching the anode, and hence we observe larger photoelectric current in the circuit. Now let us discuss the effect of potential difference. Suppose both the frequency and intensity of light is fixed, and if the potential difference between the two plates are increased, then photoelectric current increases until it reaches a maximum value. And on further increasing the potential of anode, current does not increase. This maximum value of current is known as saturation current, as you can see here in the right hand side of this diagram. Since saturation value of current is reached when all the emitted photoelectrons are attracted by the positive potential of anode. Now, what we do, we change the polarity of the battery. That is, negative potential is applied to the anode with respect to cathode. Then what happens? If we increase the negative potential, then photoelectric current is found to decrease and drops to zero at a certain value applied negative potential on the anode. Hence, this value of negative potential at which photoelectric current becomes zero is known as stopping potential or cutoff potential. So when we apply negative potential to anode, only those electrons having sufficient kinetic energy can overcome this negative potential barrier and become part of the current in the circuit. Here you can see in the diagram of left hand side, current starts to decrease with slowly increasing the potential, and at a certain value of potential called as stopping potential V naught, the total amount of current in the circuit becomes zero. So this is the point where electrons having maximum kinetic energy is unable to overcome this potential barrier. Thus, stopping potential is able to stop even the fastest moving electron. So we can write the work done by the stopping potential on the fastest electron should be just equal to its maximum kinetic energy. That is, maximum kinetic energy is equal to EV naught. So from here we can say the stopping potential is a parameter which measures the kinetic energy of the emitted photoelectron. Now let us understand the effect of intensity on the stopping potential. If we measure the potential difference across the terminal and current in the circuit at a fixed frequency but of different intensities, let's say I1, I2 and I3, then saturation current are found to be at higher values, but the value of stopping potential remains the same for all the intensities. It means that stopping potential is independent of the intensity of incident light, or we can say maximum kinetic energy of electron is independent of light intensity. So It means that with increasing the intensity, the current in the circuit increases. That is, number of electrons passing through the emitter per unit time increases, but not the energy of individual photoelectrons. Next, we will see what is the effect of frequency of incident radiation. So for a fixed intensity, when we change the frequency of incident light and stopping potential is measured for each of these frequency, then it is found that higher is the frequency of incident radiation, higher will be the stopping potential. That means distinct frequency correspond to distinct stopping potential or kinetic energy of photoelectrons. That means when we change the frequency of light, the number of photoelectrons will remain the same, but the kinetic energy associated with the photoelectron will be different. So from here we can say there is a linear relation between the kinetic energy of photoelectron and frequency of incident radiation. Now, if we plot a graph between stopping potential and frequency of incident radiation, we observe a straight line. That is, if the frequency of incident light is less than the threshold frequency, then photoelectric effect does not occur. Only when the incident light having frequency greater than this threshold frequency, we observe photoelectric effect. And at threshold frequency, that is at nu naught, the kinetic energy of emitted photoelectron is just zero. Therefore, threshold frequency is defined as the minimum value of frequency of incident light below which the photoelectric emission stops completely. How so high be the intensity of light? Now let us summarize the experimental results one by one. The maximum kinetic energy of photoelectrons increases with the frequency of incident light. The maximum kinetic energy of photoelectrons is independent of the light intensity. The photoelectric emission is an instantaneous process. That is, there is no time delay between the incidence of radiation and emission of photoelectrons. If the frequency of incident light is below the threshold frequency, then no photoelectrons are emitted. These four important experimental results are known as laws of photoelectric emission. Since classical wave theory of light could not be able to explain all these experimental results, then in 1905, Einstein explained the phenomena of photoelectric effect using Planck's quantum theory. According to Einstein, the incident light consists of a stream of particles having energy h nu called photons, and each individual photon interacts with individual electron. So, when a photon of energy h nu falls on the metal surface, its energy is used in two ways. First, a part of its energy is used in making the electron free from the metal surface. This energy is called the work function. The work function of a metal is given by phi is equal to h nu naught, and the remaining part of the energy appears in the form of kinetic energy of photoelectrons. So, energy of photon is equal to work function plus kinetic energy of electron, that is h nu is equal to h nu naught plus half mv squared. This is the Einstein photoelectric equation. Based on Einstein photoelectric equation, all the laws of photoelectric emission has been successfully verified. For further reading, please refer these books.